see you on morning session. We lesson from Professor Ostrovsky.
Thank you. Good morning. I'm glad to again see a lot of faces in this audience. I hope you still follow what happened in our course and I'm encouraged to ask questions. Who did the homework from the last lecture?
Anton.
Anton? Nobody? That's good, there was one. Just to check. Okay, so what we discussed last time, we finished the derivation of the nonlinear sigma model, which is the main subject of this whole lecture course. And we ended up with the F-shape model. The nonlinear sigma model is the model with the following action in terms of the matrix Q. Phi u over 2, so 4 integral over the whole space, trace of d double Q squared plus 2 pi omega down Q. Is it correct?
Yes.
And it's just a reminder of what we said so far. Matrix Q is a matrix of size 2n, which is written as t diagonal number t, and which lives on the closed space of the unitary group size 2n divided by two smaller unitary groups of size n. And this model with this matrix Q is usually called unitary plus model. Unitary plus. Unitary plus. So a few remarks about this theory. This model is actually very universal, and it can be seen from the fact that it contains diffusion constant inside here. So you can start with any disordered metal with any dispersion relation with any number of times, any number of very complicated Fermi surface, but long distances, at distances longer than the mean path, all electrons, the propagation of electrons is governed by diffusion equation. Diffusion equation knows only one constant d, which incorporates all the knowledge you need. The Fermi velocity, the mean free time, they are all combined inside the constant d. As soon as you know this constant, you solve the diffusion equation, you know classically how electrons propagate. And this model, which is like a quantum analog of diffusion model, it involves diffusion plus all quantum corrections that you can probably build. It's also universal, it knows only about d. It doesn't care about the actual shape of the Fermi surface or the actual number of bands. And yeah, this can be shown if I draw a line like this. I can classify the length scales. This is the axis of length, and there is length 0, which means 2 points coincide, length 0. Then there is a smallest possible length in the metal, which is called Fermi wavelength. Lambda Fermi is the smallest one. So nothing really happens in this window here. And then there is a longer scale, which is a mean free path. We always work in the limit when A is much longer than lambda Fermi, and this is actually the same condition as saying that epsilon Fermi tau as much. It's just equivalent. And in this window on the length scales between Fermi velocity, Fermi length, and infrapath, electrons propagate ballistically. This RT ballistic transfer. Now, because its length is shorter than L, so you don't care about impurities, your electrons just propagate along straight lines. And if you study a sample of the size bigger than A, they start to scatter and you have diffusion. So what happens above the C scale is diffusion. And this part, ballistic, is non-universal. It does depend on the particular distortion relation, on the shape of the Fermi surface. And on that, this is non-universal. And the diffusion part is universal in exactly this sense as the sigma model shows, that it doesn't have on the it doesn't depend on microscopic details, it cares only about the quantity like the diffusion constant here. So you can have many different metals. You can have iron, aluminum, and what other metals exist? Cobalt. They have all different Fermi surfaces. They can have different amount of disorder as long as you go to the scales longer than the Wilfrid path. They are all described with the same theory. That's why it is universal. And okay, finally, there will be some upper length scale which we will call just A. A is the upper scale at which we stop our theory, and it can be determined by different mechanisms. For example, can be the size of your sample. If your sample has a finite size, there is no reason to study length scales bigger than this. Or it can be, there can be some limitation by diffusion is limited by finite size, for example, due to frequency. This is the most simple one. Of these two numbers, d and omega, you can build a length scale like this, the square root of d divided by omega. And all these diffusons, operons, the objects that live in this diffusing window, they have omega in the denominator, and lengths longer than this, they start to exponentially decay. So in some sense, it means that if you drive your system at some finite frequency, your electrons go back and forth and diffuse one way, then diffuse back, then diffuse this way, then diffuse back. And this is the length, the extent to which they can travel. So they do not travel further than this. This is upper limit. But it can be anything. It can be due to frequency, due to temperature, and due to just the finite size of the sample. So nonlinear sigma model is the theory that lives in this window between infrapath and that scale which you impose on top. Yeah.
The question is, why can we neglect like electron-electron interactions or any other sources of like scattering?
In some cases, we cannot neglect it.
Yes, but
And we neglect it here just because it will complicate the matters a lot. But there are ways to include interaction in the sigma model. There are effects like it should have a lot of corrections due to interaction. There are very different types of interaction. There's short range, long range, cool. The basic argument why we can do it like this is the Fermi liquid theory. So you can always say that your metal is already, you took into account interaction by renormalizing the spectrum, so this effective mass spectroscopy that already takes into account, and then these quasi-particles are almost non-interactive. Those that live near the surface, so if you like, this is what we consider here. Okay, so
I have a question.
no.
So in this universal regime, what are the particles doing in diffusion? Is it the quasi-particles against the Fermi liquid theory, like the nonlinear electrons, or is it diffusons, or what is doing in diffusion?
So single electrons or single quasi-particles, if you include interaction, actually they, as I explained earlier, kind of decay on the scale of the infra path. So if you want to go to scales lower than this, you should consider diffusons. Diffusons are the proper low-line excitations of the system that can live longer than mean-free time and propagate a longer distance.
Okay.
Yeah.
We physically have a topology scale. Is it encoded in the
This A is the result.
Okay. Right.
Yeah, exactly right. Okay, so I just draw this picture to, it is not needed to understand what we do here, just to put the contents in the context of our theory. So there is some part which is not described by sigma model, which is ballistic, which is at short distances, and sigma model is an effective theory at long distances, which is universal, which does not depend on the details of your Hamiltonian or details of disorder, which type of impurities it has. Also, it's all inside N, which is inside D, and then as long as you know this diffusion constant, you can forget about where it came from. Okay, and on the last lecture, we started to consider this model perturbatively. We started to do perturbation theory, but I forgot to tell you what the parameter of this perturbation theory was. Perturbation theory.
Yes, you did not. You said it was omega.
Yeah, because omega is not a parameter. So actually, the parameter for perturbation theory, we will see later how it appears in the computation, but I can tell you already now is the coefficient in front of the gradient, not the omega. Coefficient in front of the gradient term, if you collect all these numbers, pi mu 4d, pi mu over 4 times d, somebody please tell me what it is.
Back dimensional.
One
factor.
over.
It's conductivity. This is sigma, the conductivity according to Einstein relation. Sigma is E squared mu d according to Einstein relation, and here, of course, I always drop the Planck's constant, but if I restore it, it will actually be here. Planck's constant in front of the term. So what is here? I have mu d. I have pi h over 4 sigma over e squared. So it's sigma divided by the quantum of conductance and some extra value of 4. And of course it depends on dimension. It can be 1 dimension, 2 dimension, 3 dimension. So this parameter also has dimension. For example, in 2D it will be dimensionless, and in any other system you have the art power d divided by 2, so it's length power d minus 2. And yeah. So these things should be large. And I also remind you when we discussed the scaling theory of localization, there was a quantity called G, which is dimensionless conductance of a cube of size n, which is almost the same. So I just want to say that this coefficient is actually equal to G times A power 2 minus D. So this whole perturbation theory will be a perturbation theory in terms of actually large G. Something that works in the metallic limit. When quantum corrections are weak, these quantum corrections will be exactly the result of computing these perturbations. It might be not clear right now why this parameter appears, but we will draw a confirmation and we will see that it is indeed there. So what we also did last time was we said that within this perturbation theory, we can say that the Q matrix approximately equals lambda. Approximately equals lambda. And then deviations of Q from lambda can be parameterized by matrix W, and there is some series expansion in terms of W. The W has two constraints. First of all, it's anti-collision. Second, we can choose it such that it's anti-collision. These two constraints lead us to the following form of W, and the B and minus B dagger, where B is just any n by n complex matrix. So perturbation theory means that W is small, we have this expansion, we have some manifold of our sigma model, but no idea what to draw a manifold. There's a point lambda, and the Q matrix leads to this manifold, and we consider only some small vicinity of this point lambda, and all the deviations, all possible directions are encoded in this matrix B, or in W. So this is manifold of Q matrix is on this curved surface. And perturbation theory means that we consider all the small vicinity of this lambda, which is expansion. We plug this into action, and what we did next, we expanded up to the second order, and to get the action in terms of B. So there is no first order because lambda is the minimum of the action. And we expanded to the second order, we have pi over 2 integral is R raise D, not the B dagger, not the B, minus like omega B dagger B. Then we claim that this is exactly the difference of this here. The average, the propagator of the section, B and G star, B and G, is 2 over pi mu, 1 over dq squared minus psi omega is exactly the diffusion propagator, which can be also represented with a ladder, as you usually do it. Diagrams, and there is an index I in one line and index J in the other line. And these indices actually will take n possible values, these are replica indices. So what we say is we have our disordered system, this is our disordered system, with the reproducible. And then we have a replica of it, exactly the same system with exactly the same impurities placed in exactly the same positions and not. I don't know how to reproduce this function. And we can have one green function diffusing scattered in once, replica the other one. And since the disorder is the same, there is a correlation in impurities. These dashed lines, they can connect one replica to another. Or they can be within the same replica. This I can be equal to J, this doesn't change. So, in the perturbation theory, in the lowest order, we have a non-interacting diffusors. So this is our action, it's quadratic, they do not interact. And we more or less reproduce the classical diffusion equation with the classical propagator. So if you consider the solid metal classically using diffusion equation, you can reproduce the same result from a sigma model just by going to this lowest order expansion near Q equals lambda. Now, if you want to include quantum corrections, you need to expand this further in terms of B. You will have terms that correspond to interactions in diffusons. And, for example, we already did this calculation for, in terms of diagrams, we computed the correction of the diffusion constant by inserting a loop, a Cooper loop inside the diffuson. So you can reproduce the same thing from the sigma model and you can get the same result, but not from this one. This is the unitary plus sigma model, which means there is no one loop correction Remember when we discussed this scaling laws, there were three cases. It was orthogonal, symplectic, and unitary. Orthogonal had weak localization, negative correction. Symplectic had the same positive. And for unitary, I told you that there is 0, but you have to go to the even further, even higher order, and then you get smaller, but still negative correction. So this is the sigma model of unitary class, and it does not contain operons, only contains diffusors. There are no operons in this model. That's why it's impossible to make one correction. And later today, in this lecture, I will show you how to compute this second order correction for the unitary class exactly from this model. Are there any questions? Yeah.
At what point in the ladder we are in unitary class?
See, U means unitary.
Yeah, but like from the very beginning it was clear that it's unitary.
No, it was a trick. From the very beginning it was not clear, but well, if your system has time reversal symmetry, it can have operons, and then for these operons to appear in U matrix, you have to do some extra step in the derivation, which I just omitted. And that's why they do not appear here, but I omitted it for a good reason, to make it simpler. And we will discuss what time reversal symmetry does and how operons appear a bit later. It's also in this lecture. Just let me put it this way. I cut some angle in the derivation, and the cost for this was that I lost operons, but I also know that it's the correct thing to do if you don't have time reversal symmetry. So even though my original Hamiltonian had time reversal symmetry, I ended up with a model which does not respect it, just because it was sloppy with derivation. This is really minor. Well, maybe not so minor, but we will certainly discuss it later, and then show you the presentation. Okay, so we would like to do some perturbative computation to get some physically interesting result, and that's why we will need expansion of the section to the further terms in powers of b or in powers of w, which means we also need expansion of the matrix Q to some higher powers of w. And just I wanted to remind you that there was a general expression Q is lambda times the exponential w. So this series up there was the expansion of the exponential function. And actually, this is only one possibility. There are many possibilities how you can parameterize this vicinity of lambda on your manifold. Actually, you can parameterize the whole manifold this way, but still there are many alternative ways to do this parameterization. And this exponential function is only one possibility. And in general, thing is the following. We say that our Q matrix is lambda times some function of W. It might be an exponential function. I will right now tell you that there are more possibilities than that. So lambda times function of W, it should have a certain property. This function, namely, Q squared should be equal to 1. Q should square 1, which means Q squared is lambda f of W, lambda f of W, right? And W anti-commutes with lambda, we have this expression. Therefore, this part here, f between two lambdas, is actually the same as f of minus lambda. You understand which W between two lambdas, it changes time, so it's f of minus W. So we have this restriction, f of minus W times f of W should be equal to 1. You can take any function that obeys this identity, and it can be used to parameterize your manifold. And exponent is one of these functions. Yeah, if you take exponent of W times exponent of minus W, you get 1. Yes?
Depending on this function, we're going to get different kind of boxes. how do we know which one corresponds to which?
Are they all correct? You choose the one that is convenient for you. Well, actually, I will answer this question a bit better just in a moment. So having q equals lambda times exponent means that our function f of w is this exponential function. And this is only the first possibility. This is called exponential parameterization, and it's probably the least convenient. The only reason people actually use it is because mathematicians really like the exponential function. So when they describe the properties of the manifold, they give it like this. This is exponential parameterization, and yeah, there is one other property which we also mentioned last time. When you integrate over all Q matrices, maybe we didn't mention this. When you integrate over all Q matrices with something, with your action, whatever you want to measure, it can be rewritten as the integral of a matrix W. Yeah, because Q is a function of W, so we can change variables in the integral, and then it means that we should add here something which is called Jacobian. So it's a change of variables, there is it's like a derivative, dq over dw. And Jacobian is a nasty object which I would like to avoid. That's why exponential parameterization is not very good, because its Jacobian is a non-trivial function. Then, so this is exponential. Exponential. And there is an alternative where we use parameterization with the following function f. F equals square root of 1 plus w squared plus w. You can easily check that this identity holds. This parameterization was actually introduced first by, in different contexts to different people, but for Sigma model it was mainly used by Hikami. So you can say it's Hikami parameterization or square root parameterization. Square root. It's just a name, square root. And it also suffers from the same problem that its Jacobian is a non-trivial function. I will not even compute it. It's not easy to compute its Jacobian, but I just know that it's complicated. The advantage of this parameterization is actually, it has some advantage over exponential. The advantage of this parameterization is that if you do a calculation using this function, you have Hikami boxes on its functional direction, which are exactly the same as you would get doing just a simple usual diagrams with direct and advanced function calculation that we did in some previous lectures. This is equivalent to standard diagrammatic standard diagrams. And I would like to remind you, if you were in the lecture number 3, we had this calculation of the correction to the diffusion constant. We had a loop. There was an integral over momentum inside this loop, and this integral was divergent. It contained an extra 1 in the interval, and then I explained to you that this 1 should be cancelled because there is a single diagram with an empty Hikami box and with just one impurity line of the loop around that should not be included because it's not really a correction. So actually, this is, as I say, this parameterization is equivalent to standard diagrams, and then to cancel this one, this contribution, which is apparently divergent, this exactly happens due to if you take into account this Jacobian here, then it will generate some extra diagram that will cancel this divergence. So the fact that Jacobian is not 1 actually is crucial because it allows for this diagrammatic technique to cancel all. This Jacobian is needed to cancel some non-physical ultraviolet divergences. Okay, we will not use this normalization because again, Jacobian is not one, we don't want to bother. And there is the third option, which is used in literature sometimes. It's called the rational parameterization. 1 was W equal to 2 divided by 1 minus W equal to 2. Again, this function, you can easily check, obeys the identity here. And this parameterization was first used by developers. It is one of the invalues of the sigma model. And it's a very nice thing because this parameterization has a unit Jacobian. So you don't have to care about this Jacobian factor. It doesn't have any extra diagrams because there is no Jacobian. This is called rational parameterization. And it's quite convenient because J equals 1. Then there is the fourth option. You see the images. Fourth option is the following function. It is it's square root of 1 plus W squared over 4 plus W over 2. So it's like square root of this one, but W is smaller, and then it's this whole thing squared. This function is the most convenient. Because, first, Jacobian is again equal to 1. And second, if you expand this function in series, then it contains only odd powers of W. It's called square root odd. You just take this function, you say, I want to expand it in small W in the series expansion, and you get only odd powers in this expansion, except for W squared. Just look, I will not expand it, I will just compute the square. So if I compute the square, I have 1 plus W squared over 4, right? The square of this, plus the square of this is another W squared over 4, it's W squared over 2, plus the W times the square root of 1 plus W squared. So what I did, I just expanded this square. And you see it has 1, it has W squared, and then all the rest is an odd function. It has W times the given function. So J equals to 1, the Jacobian is nice. And what is also nice is if you try to compute trace of lambda q, the term that stays in front of omega in our action, trace of lambda q, and you put q equals to lambda w, becomes trace of f of w of this function. You can omit all odd powers because w is the anti-diagonal matrix. So when you take, it has zeros on the diagonal, w cube has zeros on the diagonal, w 5 has zeros on the diagonal. So this thing is just equals 1 over 2 trace w squared. This is the exact identity. There are no further terms. So in this parameterization, the potential energy, the potential from the action actually is Gaussian. This is very nice. So I wanted to demonstrate with some explicit calculation how we can use this perturbation theory to find some quantum correction in this unitary class model. So guess which of these options shall we use?
A question.
Yes.
So do I understand correctly that what depends on the parameterization is only the Jacobian and coefficients in expansion, right?
Yes.
So why then do we need all others parameterization except fourth?
Good point. So I should stress it once again. So there is a diagrammatic technique. You don't need the sigma model to compute quantum corrections. You can just draw diagrams, as we did originally. And that's what is historically it was done fundamentally. And this can be all reproduced from the sigma model if you use this parameterization. But actually, sigma model gives you more options. You can use some other parameterization, and this calculation can become easier than doing usual diagrams. And of course, you can choose the best parameterization for you. And each individual diagram actually does depend on parameterization, but when you add up all the diagrams for computing some observable quantity, of course, it does not depend on which one you chose. Now, you say this one looks the best way. Okay, this is true, but people also use this one just because they already know how it's done with diagrams, just to double check that they do everything correctly. This is not our case. We do everything correctly without any double checking. And this parameterization is indeed quite nice for certain problems, but to answer your question, we will do a computation in the unitary class, which means we will use the fifth parameterization, which is not included here, which is even better.
No, the concept parameterization.
So there is a very special parameterization. Any of this one can be applied to the sigma model. There is a very special parameterization that can be applied only to the unitary class model. Since we are dealing with the unitary class model, I will just use it. But I should warn you that it doesn't work always. On the other hand, when it does work, it's much better than any of these. And this special thing is called Dyson-Maleev parameterization. Dyson-Maleev. These are the guys called Dyson and Maleev is an expert in magnetism. It has nothing to do with sigma model, but here, together with Dyson, they invented some parameterization, some representation of spin operators that actually can be reformulated to the representation of the Q matrix here. Now, please bear with me. Q matrix. Let's write the Q matrix. So Q matrix is lambda times this series expansion there. And I should say that all four functions here, if you expand, they all start with the same three terms. 1 plus W plus W squared is equal to 2, and then they start to be different in the higher terms. So I will also write Q in this form. So Q equals lambda is 1 minus 1. This is when we have no deviations. Then we should add lambda times W to the linear term. And W is B minus B dagger. We add it, we have B dagger. This is linear deviation of Q from linear in B. And then we should add the quadratic term, which is 1/2 W squared. Take this W squared, multiply with lambda, and we get minus B dagger over 2. And here we have plus B dagger B over 2. So far, if you have a matrix with just these four elements, it's the same as the one written up there. Q is lambda times these three terms. And now I should add a cubic term. The cubic term does depend on the parameterization, on the one that we chose. And as I said, I will now choose a different one, not written over there. And the cubic term that I add will be the following: minus B dagger B divided by 4. That's all.
So can you write Dyson-Maleev parameterization explicitly? Or
It's written explicitly.
I mean, but this is only to the third term, right?
This is exact.
Ah, this is
Now,
exact.
the claim is
Okay.
This is exactly not need any further terms. If you take this Q matrix, you can, this will be a homework that I will never check. You can easily find out if this method squares to it. Yes?
How does the calculated population for calculation?
I did not calculate it in Jacobian.
Yeah, I mean, it's like one-dimensional function. So how do?
Well, it's not so easy. Jacobian is, well, I can give you a precise answer. Not approximate, precise. This model is defined on the perfect space. This model it is defined on the space Q squared equals 1, some kind of sphere, many dimensional, it has a curvature. Therefore, it's the question is how we define the measure of integration in this curved space. And this question was actually answered by probably Riemann in the 19th century, and then the answer was used by Einstein in the general theory of relativity. I will just give you this answer. Sorry, I didn't get that finish. So to define the measure of integration, you consider the interval. As in the theory of relativity, you have interval in your space-time, and the interval dA squared on the manifold is defined like this. Trace dQ squared. You have some differential of your Q matrix, you square it, you take the trace, it's the distance. And then you write this Q matrix in terms of W, and W has individual elements as the variables of integration, is dW as the element. So you should compute this trace, and you should write it as some matrix G, two indices, dWi, dWj. So it's a quadratic form. You can find the matrix of this quadratic form in terms of W. And then Jacobian is the square root of the determinant of G. This is called the metric density.
So W is a vector, right?
W is a matrix.
Matrix? Okay,
So this,
all the separations.
it's a matrix that has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Just some variables inside it. It's a set of variables. They are arranged in a matrix, but you can enumerate them just with one index. Doesn't matter how you enumerate them, the determinant does not change.
So this formula actually has matrix.
Well, then I write dq without any explanation. Actually, I mean the integration with a proper measure in the curved space.
Okay.
Now, Jacobian, which is this, to tell you the whole truth, is never unit. This Jacobian is always some non-trivial function of W, but it can become unit in the replica limit when you take n to 0. It can become unit when it becomes non-trivial. So when I say J is 1, I mean in the replica limit. There was Phil?
Yeah, is it okay that Q is not recognition?
I will answer later.
We need to define this transformation. We only need to specify this in zero order. To define F.
No, we need to satisfy this.
In zero order, right?
Into all orders. F should exactly satisfy this condition, then Q square will be exactly 1 everywhere for any W.
But the first is already E minus.
This function, F of minus W times F of W.
Okay, yeah.
Exponent of minus W, so W is 1. About the hermeticity. This is a good point. So, Dyson-Weyl parameterization is none of this because it cannot be written in terms of W. It is written directly in terms of B and B directly elements of W. And the reason why, whatever you write in terms of W, anything like this will be automatically a Hermitian matrix, as the Q matrix should be. And this matrix is explicitly non-Hermitian, it has two very different blocks. So, Q square is equal to 1, but Q is not equal to Q terrible. This happens, this implies this parameterization only And now the question is why should we integrate? So we did something bad. We had original initial methods and then used parameterization that breaks this thing. And the answer is we don't care. We don't care because we have many examples when you have an integral over some variable, real x, real integral, and then Cauchy tells you that to compute the integral, you can actually deform the contour and remove it from the real axis. You can, unless you, if your contour does not pass through any singularity of the function, the integral is the same. So Q equals Q dagger is this matrix analog of the statement that Q is real. And when we break Q not equal to Q dagger, we make it complex in the matrix sense. Now, if it's one by one matrix, Q equals Q star is real. So if you like, the integral over the Q matrix is the multiple integral of all possible elements of this matrix, of all possible parameters, and we can deform contours for every of these integrations. So as long as we integrate from minus to plus infinity, it doesn't matter if we go exactly along the real axis or we go along something else.
Why is there no singularities?
Or, no idea. Let me put it this way. We will do perturbation theory. So what we will do will be actually a Gaussian integral with some great exponential. And this whole thing will be relevant only near the peak of this Gaussian thing. So for small values at least, like an expansion. And it means that as long as your integral converges, you can always continue your contour to infinity to make it valid. And in this small vicinity, there are no singularities. We will not say that. Yeah.
How can we see that, like, now manifold, instead of living, let's say, in real space of Q's with real coordinates, we extend it to complex ones, and we say, okay, Q equals Q dagger is not essential, but why Q squared equals 1 is still essential? How can we see that? Because I can just say, okay, I'll deform it to something that is not Q squared equals 1.
Well, originally we have Q equal to Q dagger and Q squared equals 1, and we have an integral. Then it's just a question of how we compute this integral. We compute it by deforming the contours such that we break this identity. And however you deform your contours, you will never break this identity just because it is incorporated in the parameterization. Well, if you like, you can break this as well. Maybe you could not, but no, we cannot do that. I cannot answer your question because I just cannot imagine how you should do the integration such that this condition should be based on. If you look, we had this Q squared equal to 1, it was maintained by the conditions on the double conditions.
Yeah, but this squared relation is not in terms of W, right?
Well, you can rewrite it that, so in terms of P, well, yeah, you're right, it's not in terms of W. Okay, so you want to suggest some other form of the matrix, which will be non-Hermitian and not squared into 1. I'm not sure that.
Because, I'm just trying to understand why, what are the fundamental reasons where I cannot just write some arbitrary things in each cell of Q and that's it? What will stop me from doing this?
Take it from your manifold now.
Yes, but we already broke it.
Well, let me put it this way. Q and Q dagger involves complex, this operation involves complex conjugation. So when you say Q equals Q dagger, you impose some condition that relates to complex numbers. Something should be equal to its complex conjugate. And when you deform the contour in the complex plane, you break this relation. But Q squared equals to 1 is purely algebraic constraint.
Okay, this I like.
That's why it's much harder to break. It does not involve complex conjugation. computation. So whatever you do with your controls, it will not be broken. You have to introduce some new variables that are not originally there. Then you can use. But then you will get the wrong answer. Okay, so Dyson may once again works only for unitary class, only unitary. But since we so far have only unitary class we don't have, it looks very strange first sight because it indeed violates the hierarchical methods. But it's very convenient for computation, and also I forgot to mention the Jacobian is in unity. So let's do some calculation. I take this few measures. It's very simple because it's just a finite polynomial up to the third order of normal terms. And I plug these geometrics in my action, that one upstairs, and I erase some part of this mess on the board. Actually, I don't want to erase anything. I already have my action up to the second term, and it's the same in any parameterization, it's the same thing. Even the Dyson matrix is still the same because up to quadratic terms, all parameterizations are equivalent. And as I promised, there are further terms here, and for Dyson matrix, for unitary class, the next term is d over 4. It comes from the gradient term if you insert over there. B dagger, nabla b squared. This is the exact action. I mean, this original expression here, you take Dyson matrix Q matrix, you plug it in, and you get quadratic term, and the term of the order 4. 4 is inside, and nothing else. There are no higher terms because there are no higher terms in Q matrix. So what we have is an effective series.
Yeah, I ask another question. So when we use this parameterization, we parameterize the whole manifold, or we try to parameterize on the closest region near Q equals to lambda.
We parameterize the whole manifold,
The whole manifold.
but then we will do the integral, which will be mainly determined
Yes.
by
And how can we see that we actually parameterize the whole manifold with this?
That's a good question. And it has an answer which I am unable to present. It's a complicated calculation. And actually, it requires some extra restrictions on what matrices we use. But for calculation theory, it doesn't matter because
we're
will end up.
Okay, then just how to think about that question. All the parameterization you mentioned before, they had like some non-linear functions in W or in D. And here we have only like some finite, I mean not just non-linear, but also some non-power functions. And here we just have like third power in B, and that's it. Like how to think about that? I mean, if it just parameterizes the close vicinity of lambda, that's okay. But as far as you claim that we actually can parameterize the whole manifold, it seems strange.
As I already said, it's not easy to think of this.
Okay.
That's why I will not present. But it's possible. I mean, I can give you a paper where this question is discussed. You will read it and then explain me how it is done, because I don't understand. Well, actually, I did understand once, but forgot what it is.
Why does that work on for the unitary class? No.
Because in other classes you have some other constraints on Q metrics that you compare in this form, and which are algebraic constraints, not the relation between them. Well, actually, it is applicable in some classes, not only unitary, so classes C and D, which would have. So in some sense, in unitary type classes of unitary type, they are still. Never mind, for the simplest situation, we move on to this one. Okay, so let me continue here. I update the action. Now this is the exact expression. It's a quadratic part which has this propagator, and there is only one possible type of interaction, which is this vertex here. And this vertex here is called the box, as usual. It's like this. I already mentioned it last lecture. It's the interaction of four matrices B. So it's B together, B together. It's a trace superproduct. And it also has two gradients, which act on B. The gradients here in my poor diagrammatic representation, I will show by a dash. These two things are crossed with a dash because there is a gradient acting on them. Acting on this matrix, B, and this matrix. This is the only interaction vertex in the Dyson-Meyer parameterization of the unity class. And this vertex is proportional to the same thing, pi mu over 2 g over 4 up there. So we can use this theory. We can now compute multiple corrections to the diffusion constant due to this interaction. And the lowest possible diagram actually includes two such vertices, because if you insert only one, you have B bedecker, and this B bedecker you should connect with the diffusor, and then summation of replicas gives you B. It's proportional to the number of replicas. And this is exactly what it should be, because in the unitary class there is no one-to correction. One-to correction was only possible to cooperants. There are no cooperants here, that's why there is no one-to correction. Already said many times. So we need two, which means two vertices like this. And I will probably draw it here. So we have one vertex. This is a nice picture, but I'm not a very good artist. This is one vertex with two dashes like this. And there is a second vertex with the dashes here. This is the ladder that comes in. This is the ladder that goes out. And I should connect this to this with three diffusons to produce this self-generation. And the proper way to connect is the following. I connect this directly. And this other one, I actually connect here to the lower. So it goes like this. And this lower one, I connect there to the upper one. So these are three different things. Clear what was supposed to express. This picture should be more. So this is the continuation of this, that one is the continuation.
Each of line is a diffusor.
Each of this
Yes.
ribbon is a diffusor.
How do we connect this diagram with the trivial one?
It's quite easy to understand, because this is something we always do in this diagrammatic calculation. We avoid to have detached Fermat loops. Look, we have a Fermat line, it's like a return function coming here, and you can trace it. It goes here, here, then here, then here, then here, and then goes. And the second line also does this figure 8 and goes out. There are no, for example, if you try to do a one loop diagram with diffusor, you will connect it like this. And say this is a correction. Then it has this loop, this single Fermat loop inside, which is attached to the rest. Which cancels due to the replica limit. Now, if you connect, for example, this to this, and then the upper one to upper one, you will have the similar loop. So this is the only way to connect such that it does not cancel.
In the ribbons twist. In the ribbons twist.
Ribbons can twist, but it's just a pictorial propagator of the matrix B, which has indices, and indices propagating along the lines. So when you connect them, you have the trace, which so indices should be connected in a certain order. So if you twist your ribbon, you can erroneously take a transposed matrix B, you interchange the indices. Sometimes you have to do this, but in this plot, it's the only way to connect because you avoid these transpositions. Okay, so just I have too many lines here, and I should make this line like this one. This is a gradient, this is not an impurity line. This is a gradient. This one is a gradient. And all the others are just diffusons.
Sorry, why you would connect the ones with gradient with the ones without the gradient?
Because we always connect B to B dagger,
Yeah.
and gradients are applies to B, and not to
And
just, we did not do this calculation earlier, but we can also compute quantum correction to diffusion constant in using usual diagrams of diffusons as we did for the Cooper diagram. So you can do a simple diagram without a sigma model, but then I should warn you that in the usual diagrammatic technique, in the unit class, there are two diagrams. In the usual, with the usual representation, there are two diagrams. There is a second one which involves a Hamming box with 6 diffusons. There is a Hamming box with 6 diffusons, and then you also can connect 4 of them, so everything works. But in this Dyson-Molev parameterization, there is no high-order interaction. Therefore, it's very useful here because it produces only one diagram. And if you use the one that I just erased, the Hamming parameterization, you will get 2 diagrams. Both diagrams will be quite divergent. But when you add them up, the main divergence will cancel out, and then there will be a smaller contribution that will give you the final result. And it's a very hard calculation because you need to compute the integrals not to the leading order, but to the negative to the leading order, because leading order finally cancels. In this calculation, it will be much easier because we just compute this diagram to the leading order, and it gives us already the correct result for the quantum correction, and correct result for correction. And I will do this calculation right now, but first I ask the audience, how should I do this? Does anybody have suggestions how to compute such a diagram? Yes?
Could you explain again these diagrams to diffusons that connected to what?
Actually, there are 3 diffusons.
Okay, 3 diffusons. That's
This is the interaction where the diffusons are propagated and interact, they collide. And whenever you have this cross like this, 2 diffusons came, collided, and go on. And then there was one diffuson that propagated. Then there is this interaction vortex. There are 3 diffusons. They interchange, interact again, and become a single diffusion again. So this is the process.
okay.
It's a diffusion which interacts with itself. It goes here, when it returns, interacts with itself, goes forward, interacts with itself, and then it goes. Well, it's just, of course, it's not a real process. It's just the way to think of it. So real diffusons do interact, but they interact only as a result of Dison average. In any given sample, when there is no Dison average, there is no interaction. Only when you include something average, it's effect and interaction. So, this diagram has 3 diffusons, each has its own momentum. Also, there is a diffusion that comes from infinity and goes away, which also has its own momentum. There are integrals of momentum in one line, in the second line, that's a double integral. How should I do this? Any ideas? It's a complicated expression. I don't even want to write it. It has 2 loops, it has 2 integrations, so 2 different momentum.
We should first calculate the loop, then because it does not have.
This is an interesting idea, which doesn't work in check negatives. doesn't work because these two loops they have one line which is the for loop.
Okay.
So if you have momentum in this line and this line, then in the middle one you have the sum of them. Integrate with one, integrate with the second.
Okay.
This
But
is
wait, why do you attribute momentum to just a single line if you're already working with diffusions who are themselves independent object and they just have a common momentum?
okay. Let me show you. So imagine there is a momentum q which enters from here.
Yeah.
And then I will just vigorously say this momentum goes from this line and goes on.
Okay.
Then there is a momentum capital Q1 that goes in this diffusion, and capital Q2 that goes goes over this diffusion, Q2, and then they all add up here, so the momentum in the middle is Q plus Q1 plus Q2. Then you add this gradient, which means Q times Q plus Q1 plus Q2 times Q1 times Q2 times. And then you integrate over Q1 and Q2, and the problem is that you have a diffusion which are they both.
No.
So it's only one diagram, not two diagrams, but it's still not so easy.
And you have three diffusons for two integrations over Q1, Q2. You just write down the integral and then you calculate it.
This is a nice idea, I tried. I will give you as homework personally for you. Any other suggestions? There is a trick how to do it much easier.
I mean,
Again, by self-redrawing, probably.
I mean, we have obviously symmetry, like if we switch Q1 and Q2, it will be the same diagram, right? So probably
Yes.
we can use it somehow.
So the integral over Q1 and Q2, the integral is symmetrical.
Yes, yes, yes.
So you can say it's twice the integral on Q1 is larger than Q2.
Okay.
Okay, so you had some time to think about it. Now I will give you the answer. It's the easiest way to compute this diagram is in the real space representation rather than in momentum space. Because in real space, so in momentum representation, it has two loops. It has momentum moving inside each loop. It's a double integral. In real space, it has only 2 points. Point here and point here. And the three diffusons connect the same 2 points. So it's only one integral of the distance between these points. So to do calculation in real space, to do a Fourier transform, we need a diffusion in real space. Who knows how the diffusion looks in real space?
Sure.
It's in real space and real time.
That is close, like
In real space and real time. So diffusion in real space. Diffusion propagator. Well, actually, I will call this thing of diffusion propagator up there. Diffusion propagator in real space is of a distance r is pi u over 2 integral over the whole momenta. Now I do the calculation in 2 dimensions. 2 dimensions. All my momenta are 2 dimensional. And I write d2q divided by 2 pi squared dq squared exponent of pi q bar. This is the Fourier transform. And I draw omega for synthesis. Well, actually, it's plus minus omega here, but let's assume omega is 0. Omega, as I explained at the beginning of this lecture, omega defines the upper limit, the longest length in our problem. So if I consider, for example, a finite size sample, and omega is very small, I can just draw it. So it's this integral over q, and you see it's 2 q's in the numerator, 2 q's in the denominator, which means it's logarithmic. And logarithm, it diverges at large q and at small q. At large q, the logarithm is limited by this exponential factor which starts to oscillate and kills it. And at small q, the integral is limited by omega. If I reinstate omega here in the denominator, it will cut small momentum. And let's say I want to cut it with a with the size of the system. Sorry, the size of the system is my lower limit.
Question. Last lecture, when you were speaking about activation theory, you said that omega has to be not very small, right? Now,
And that was wrong. I apologize. Actually, perturbation theory works on the large values of G.
yeah.
The large.
Okay, and how exactly do we use this big parameter now when we expand? So we basically expand the x1, right, and take the second order of this term. Where exactly we use the small parameter?
We have two loops here. We have 3 lines and 2 vertices. Each vertex has also diffusion constant. So it has this large G in the numerator.
Yeah.
And each diffusor has diffusion constant in the denominator. So we have 2 vertices times 3 lines is 1 over diffusion constant. That's why large diffusion constant is small. And it's just the you just count the number of loops. Each loop gives you an additional smallness of 1 over diffusion constant. 1 over G, dimensionless conductance. Okay, so for small values of Q, I can limit it with omega, or I can limit it with the size of my system. And for large values of Q, this exponential will cut everything. So it's a very simple integral. I don't compute it exactly, I just say it's minus pi squared mu d. It's a collection of all the numbers. And then it's a logarithm. It's a logarithm.
Where do you get other nu in the denominator?
R divided by A. Sorry?
Where do you get the nu in the denominator that of the numerator?
Not because I'm stupid, it was 4 I knew, and then I write I knew it. Actually, it's 2 over I knew. It's not that.
Can I ask a stupid question? Like, why again do you need to draw it like this in this diagram? Why not just 3 parallel lines?
If you draw parallel lines, this is what you get. You have detached Fermat loops inside. 2 of them. This line is not attached to anything outside. And this line is not attached to anything outside. And each line has a replica index on it. And then if you take the trace, you sum of replicas. This means that this diagram will be proportional to the number of replicas squared. Each loop gives you another number of replicas. Then in the limit, 0 replicas, it will disappear. This diagram has only 2 lines, there are no closed loops. This line that comes from the left does the hyperphase control, and the second line does the same. All lines inside are connected to the outside.
What are these diagonal lines on this diagram?
Which lines?
Diagonal lines on the diagram. So I guess it's
This?
gradient, right?
Yeah, it's the gradient.
Yeah, and why did you choose it this way? So why not like horizontal?
Because they are, if you look at the action, it's b diagonal b squared. They all always act on b and not on b dagger. On the trace, I have b dagger, b dagger. They should always be one across the other. And the diffusion, the propagator connects b and b dagger. So I always connect the line with the dash. There is no dash.
Okay.
So, sorry, is this clear? I mean, the diffusion. The diffusion of real space is just a logarithmic function of the distance. Yeah.
Why is the small scale of Q independent on omega?
This A, as was introduced in the beginning of this lecture, is just the infrared cutoff. It can be a square root of d over omega, or it can be a system size, whichever one is small. I just don't specify what it is. So I remove omega from here, and then I introduce the cutoff, which can be either due to omega, which is a system size, or due to temperature. Okay, so this is this thing clear for the diffusion? Is it? No? Okay, so now we're using real space representation to does. I call this diagram as usual by gamma. It's not gamma. Now I will write what gamma is. This is for omega equals to 0. For a system of finite size A, you can, if size A of the system is smaller than this case,
yes,
you can
yes.
neglect it. That's why I don't need this misleading. There is no frequency 0 system of finite size. And this is the size of the system. Okay, so first thing comes first. Pi mu d over 4 squared. Just each vertex here is pi mu d over 4 from the action. There are two such vertices. It's pi mu d over 4 squared. And then there is an integral of a two-dimensional real space distance. Distance between this point and this point. And this integral should be a Fourier integral. So what I'm trying to say, I will write it then erase because it will be a wrong equation, just to give you an understanding. I will write dq of r, 3 diffusons, and then I will do a Fourier transform for minus I r. This will be the r integral, depending on q, it will go. So this is what I will write. But since I also have some gradients inserted there, it's a bit more complicated. Namely, actually, it's almost correct. I have lambda d squared. I have this upper diffusion and the lower diffusion. Each one has its own gradient. And this is a scalar product of these two vectors. Inside each vertex there is a scalar product, so this is scalar multiplied by this, so it's gradient to this point. And the third diffusion of this one has a scalar product with the outer line, so the third one will be like this. I q lambda g. And this is the q, the same as in this exponent, and this is the q on which gamma. It's the external element.
Why is it IQ and not minus it?
This is a good question. There is a overall minus. So this is the integral over two-dimensional integral over r that will produce this gamma. And I should insert this d, which is just logarithm, into here. But there is also one other thing, namely I need only small, I consider this whole thing for small values of q. My external momentum is small. Therefore, before doing this integration, actually you can approximate this exponent as 1 minus I q r. You can expand in small q.
What is the integral for d by q?
Can you say
Why is that integral for d of L group like this? Shouldn't be the
This one.
squared minus I omega, right?
I already repeated it many times. There is minus I omega. But the integration is limited by the system size. The system size is large, so it's small compared to this scale square root of the omega. That's why I can omega just, look, this is a logarithmic integral, and omega just defines the lower limit, which cuts this logarithm at small values of q. It can be also cut by system size. And if system size is a more important cutoff, then we will do it. And if omega is the most important, then this A will be just replaced with this omega dependent thing. But, yeah.
So we exclude omega from the expression, but like in the initial diagram, the transformation of a moment that one can do, why don't the transformation of the frequency on the one and on the two?
But there is fixed.
Because omega is just a parameter of our action for the very first and the static derivation of the signal. We have just fixed energy in our green function, we have a fixed green function, and omega is also a fixed parameter, there's no integration anywhere. Okay, so this is a very simple thing. Integral of R involves integration of the directions of R. See, this D is isotropic function, depends on the absolute value of R, and this Q is vector. And this lambda goes along R, so when we average over the direction of R, we have to take this linear unity that will cancel out the integration of the directions, and what we get is the following thing. I can either do it from the board or minus phi mu d over 4 squared. Then we have q bar times q lambda. So actually I do have some details, but in some way so. Who knows how to compute derivatives? What is number of degrees? Number of modules. It's like 1 R squared phi squared mu d, and then I have R divided by R squared, right? And look, A doesn't enter here, so even if you had omega originally and then it depends on omega, it cancels. Nobody cares. So this should be inserted 1, 2, 3 times, and then I get all this in the denominator. Pi squared mu d whole power 3 such differences. Pi squared mu d power 3 integral 2 pi r dr. This is a two-dimensional integration of r. Then I have gradient squared, which means r squared divided by r to the power 4, r squared in the denominator. And then I have minus I times I is 1. I have qr from here, and from here I have q times this r. I have qr squared divided by another. And I already lost track of the overall coefficients. Probably it's minus.
Maybe
Yes. Yes, you do this.
You have three derivatives and one minus from minus IQR, so it is still minus.
So it's plus.
But why?
It was minus originally.
Yes. And you have
And gradient is minus.
yes, and you have one minus from exponent.
Minus I times I.
Yes.
Plus
Plus.
1.
Plus.
And then I have 3 different ones and each contribute to minus. Plus.
3D.
Just plus.
Yes.
Okay, and the final thing to do is to average the directions of R. I have this QR squared. When I average, I get in 2 dimensions. Correct? One half Q squared, R squared over 2. And this whole thing ends up equal Q squared, so Q squared is divided by 16 pi 16 pi q mu d integral dr over r.
What's the need to write 2 pi r dr if you need to average over angles?
Or you can write the integral over phi instead of 2 pi over n. Or you can write 2 pi and then say this one is averaged.
Okay.
So this I just copied from my notes, but it should be the same coefficient. And just to write this result explicitly, gamma is q squared divided by only 16 by 2 mu e logarithm of r, which is, sorry, logarithm of a divided by small a. System size infinite. The same way we had our logarithms for other loop diagrams for coupons. We said that there is a system size on top, and all the diffusion starts from the scale of the mean three paths, so the Q, the largest possible Q is in plus A, with the smallest possible R, smallest possible R is A, largest possible R is the system size. This is and the most important thing is this Q squared in front. Q squared is very important because it should be 0 when Q equals 0. And it should be a correction to the diffusion constant. Now, if I insert this gamma in the denominator for my diffusion, it will correct, it also has Q squared, it will do a correction to the diffusion constant.
Can you please remind the typical scale of Q once again?
So, of the width of this Q,
yes, of the.
it's somewhere inside the diffusion limits. Like QL is small, sorry. Yeah.
But if QL is big, QL is big, if we're in diffusion, QL big is big, right?
Maybe.
If why can we expand up?
When we calculate it, we put them in coordinate.
Well, look, this interval here is the interval over the distance between two points. Is this is from the elephant up to the system size, even if your external view is anything it likes to be.
Exactly. Okay, and then why we can expand exponent?
This one?
Yes, because R can be of the size of L big.
So actually you can retain the exponent, but then all time terms will not logarithmic.
Okay, yes, okay.
So this is the main contribution.
Yes.
They will have extra powers of R, they will be all ultraviolet, they will. So,
Yeah. The high terms would be the version of the big R.
It's a tough question, actually. The problem with them is not they have large R, the problem is that they have high powers of Q. So you can have corrections, but it will be not Q squared, it will be Q to some power, which means you do not correct the diffusion constant, but you introduce vertices of more than 2 gradients, and these vertices are actually irrelevant. Irrelevant in the RG sense. I don't want to go into this detail.
Yes, no, I would.
My point was not to compute it actually exactly, but to extract the coefficient in front of Q squared. And this is a correction to the diffusion constant, and it's quite easy to understand what it does. So, correction to the diffusion constant, delta T. I should take this whole thing and add it here, so I should remove I more of 2. So it's minus Q squared minus 4A over A divided by 8 pi squared 8 by no, it's vice versa. So 5 power 4 mu squared and now I can use the Einstein relation and write the correction to conductivity. Delta sigma is P squared mu correction to the diffusion constant, and it's negative. Gamma is positive, but when you put it in the denominator, it's minus gamma, so the correction is negative. And it is minus more than A. And then this whole thing in the denominator, I can combine into one x plus sigma. Because mu times t is sigma, according to scale Einstein relation, so it's logarithm divided by 8 pi to the power 4. So, sorry, this is mu squared, and the delta sigma I multiply by nu, so I have only one nu denominator, and it's not. Yeah.
This is already quantum. This is a quantum correction.
This is a quantum correction to conductivity in the unit of class.
So how is it in order of h?
Sorry?
Is it in order of h? How do we see that this is close to 0, h is 0? Or it's not
So I
like
don't understand what is H.
h bar. I mean,
H bar.
Yes.
This is sigma, so all sigmas here are measured. Well, in this expression, H bar is 1. You can restore it, then you will see what happens. Actually, I also know P squared, that's the problem. So, let me put it this way. This is correct, now the sigma equals to this if you measure sigma in units of E squared over H bar, if it's dimensionless. Then one-dimensional string equals the other dimensions. I can even, but then this is intermediate for this talk. Okay, so just to remind you, we have this scaling theory, we have a beta function, d log sigma by d log a, was a function of log sigma. Sigma and g is the same dimensions. And now if you take d log sigma, by d log a, you will get something negative. So you will have a negative correction here, and this proportion, this negative slope, is proportional to minus 1 over sigma squared. Because when you differentiate log sigma, you have delta sigma over sigma, and then you have another over sigma for here. It's 1 over sigma squared. So it's small negative correction opposed to a usual Cooper diagram conclusion for total class where it was just minus 1 over sigma without this square. So with the distinction, we have an extra sigma in the denominator, which we didn't have in the total class. Extra dimensionless conductivity, and this dimensionless conductivity is actually our large parameter here, and this defines how the computation theory works. So it's a small correction, provided sigma is large. Yeah?
And we got the quantum correction to our action.
It's an accident also.
That depends on the computation. When we got the quantum correction to action, that depends on the computation.
Well, it does depend, but if you rewrite this all back in terms of Q, it will be just the corrected values of D and omega, and it should have the same form in terms of Q as it was before we did this calculation.
But does that mean that the answer depends on computation?
The answer is for sigma, or for the diffusion constant, for the coefficient in front of number Q. Doesn't matter how you would represent your Q matrix, the coefficient is always multiplying number of Q squared. And this coefficient gets correction. This is actually conductivity is the measurable quantity, it's observable quantity. It should not depend on any mathematical assumptions you do, like parameterization or gauge choice or whatever.
Okay.
But individual diagrams may depend, because you should add all possible diagrams for the quantity, then you get a result that does not depend on the parameterization. But in this Dyson-Mallet, the nice thing is that it's only one diagram. Yeah? Yeah, please.
Here we will correlate conductivity from Einstein relations, but is there any way to put physical quantity into this sigma model? Because it's formulated in terms of V and calculated with formulated.
I claim, and you can argue with me, that diffusion constant is a physical quantity, not worse than conductivity. It's already in the action.
Okay, if I know some operator, and I want to work the average of some operator.
What do you call operator? Is it
something that I can formulate in terms of electron creation and destruction?
okay? Yes.
I have some functions, and can I put this operator into the sigma model?
You can express, you can retrace the derivation of the sigma model, and you can rewrite your operator in terms of the Q matrix, and finally in terms of the P's. Then you say I want to average some combination of B fields with this action, and this will give the answer. I just gave you the general recipe. It's just too general, and if you give me an operator, I will tell you what it is in terms of B. Yeah, actually, I wanted to say that this is all for today, and if you have more questions, maybe we should not keep the whole video sitting all the time. So, thank you.